Hi everyone, this is Group 6 and welcome to our He Smart Orkney case presentation. Here me, Rong and Siqi will show you a detailed analysis from our team regarding the demand response DR schemes, financial viability in terms of both financial benefits to our company and to the whole community. We will start by first exploring the current energy curtailment situation across the island. Then we'll show you the implementation outlook from different levels of DR penetration. Finally, we will show our assessment of the project's financial viability before concluding with our investment suggestions. First, to find how much energy is currently curtailed annually across Orkney, 3 models have been built to simulate the situation in 2021. The general idea is that curtailed energy equals to theoretical maximum output minus consumed energy minus exported energy. Now let's begin with local demand. We can see there is a seasonal trend that was high in winter and low in summer. Also, the highest mean load was around 0.5 kilowatts. Then, since we find the household's demand changes constantly during a day, we divide the time of day into 4 stages with 6 hours each. We can find the highest mean load is around 0.43 kilowatts. In order to estimate the 2021 level and transform these patterns into a series of parameters, we assume there would be a 20% increase in local demand given the rapid development of electrical cars. Then we multiply the simulated highest mean load by the series of demand parameters achieved previously to get the actual energy consumed for every 30 minutes in 2021. Next, let's move to wind speed to power model. We find that wind speed and power output are highly correlated but not exactly linear. We use a piecewise model which provides a pretty good replication of the power versus wind profile. For example, when the wind speed falls into 8.8 to 9, the corresponding theoretical maximum output is 350 megawatts. This means the turbine can at most achieve 39% of its installed capacity. We assume the same wind speed pattern in 2017 as 2021, and around 10% of the turbines work at one time on average. In addition, we assume that 20% of these working turbines are located in the region where wind speed is weakened by 30%, and here is our theoretical maximum output. Finally, we find the annual curtailment for 2021 is around 30,000 megawatt-hours after considering the 40 megawatt export constraint. This represents nearly 13% of potential production, which provides great potential reduction that we could achieve from the DR scheme. Now please let my teammate Rong show you the implementation outlook from different levels of DR penetration.
Based on the previous section, we have known that if no measures are taken, the curtailed energy would be a huge waste. Fortunately, the tree of DR scheme was purposed to control the household demand through which reduce the curtailed energy. As a provider of such technology, the first step is to estimate the total value that might be generated from this scheme by different levels of DR penetration. Firstly, let me introduce how the system works. There is a controller inside the storage heater to control when it should be charged. When there is excess energy during off-peak hours, the storage heater will be charging and therefore use part of curtailed energy. Then during peak hours, households will satisfy their demand with the energy stored in the heaters. Based on this mechanism, we built our DR model. Here we come with several assumptions to simplify the model and simulate the real-world situation. Firstly, we assume the storage heater used in this project would be quantum heater with 1.1 kilowatt input rating and 17.7 kilowatt-hour storage capacity. Secondly, based on the data in 2018, we assume 75% of households currently use electricity for heating and the remaining use oil or others. Thirdly, we assume households who originally use oil or other for heating would have the same demand pattern as those currently use electricity for heating. Fourthly, to maximize the reduction in energy curtailment, the household would use the storage energy only when the output could not satisfy their heating demand. Lastly, the storage heater would be charged only when there is excess energy after satisfying the local demand and being exported to the mainland. Then, we simulated the system. We could find the ideal situation is when the DR penetration is 100%. The reduction could be up to 8,000 megawatt-hour. If half of the households could participate in this scheme, there will be 14.26% reduction. Even with a 25% DR penetration, we can still achieve the reduction of 7.7%. Now we may ask how much of this waste energy could be monetized. Please let my teammate Ma Siqi to show you our assessment of the project's financial viability.
Thanks, Ron. Now I will explain to you the financial model and analyze the profitability of the whole program values to the community. Here are basic inputs for our model. As you can see, we assumed 10,541 households. 65% of users use electricity for heating. And we also build the financial model based on some variables like the average price of electricity and oil to do the on-site services. The 4 demand response levels are flexible towards households, wind farms, and cruiser. For different demand levels, we assume different profit margins and government subsidies accordingly. Now, we look at the cost and saving of the 3 stakeholders of our model. Firstly, households. The cost here is heating charges, and the cost also have to purchase an upgraded device from cruiser. For savings, the household get from the government subsidies and discounted price on the energy that was curtailed but now saved. From the table, based on different demand response levels, we can see corresponding local households who decide to equip devices. And the larger the proportion, the greater net value they will achieve. Let's consider the wind farms. The major suppliers of wind power. Profit is from wind power sales. And for the costs, the fixed costs like insurance, rent, maintenance, and so on. In addition, the operation and maintenance cost is calculated in this way. From the bar chart, we can see that the more electricity to sell, the more profit the wind farms will gain. Moving to cruiser, not only benefit from the social reputation, they will also get actual revenue for promoting renewable energy and doing the HSO project. The revenue mainly comes from the device sales and government fundings. For the cost, here 3 types of payouts in our scenarios. The first one is the cost of production, the second is labor cost, and the cruiser also needs a budget to do ad campaigns to increase brand awareness, and then the DR penetration. As a break-even analysis, and the chart shows that the higher the DR penetration, the higher the break-even price should be set. This means that the variable cost and on-site services outweigh the increase in device sales. Finally, we use the net value analysis on the different demand response levels to consider the feasibility of this project. As we believe, the project will be appealing only if all of the stakeholders find their own economic interest. Typically, the total benefit and energy saving increase gradually as the demand response level increase from 25% to 100%. This program will bring at most this profit for the stakeholders, and the 13 households choose to equip the high-tech devices. For the whole society, nearly 1 million points will be generated as long as penetration is over 25%. For cruiser, the profit is around 0.4 million when DR level reaches 25%, and the ROI is about 15%. Therefore, the program is considered to have potential and worth implementing. Okay, based on our analysis, we monetize the saved energy with DR penetration to test the feasibility of the program. So first, if the program provides more than this profit for Orkney, so yes, we suggest invest. Second, we believe it is necessary to conduct marketing campaigns, or it may not be influential enough for the society. And to consume all the curtailment, the higher their penetration will bring more profit. Choose appropriate demand response can make a win-win result for all stakeholders to find their own interest. We suggest broaden the consumers if this project is implemented. However, we need to admit that our model involves some risk. We assume project isolation and a stable export electricity demand, but the reality may not be the same in the future. That's all for our presentation. Thank you for listening. If you have any questions, please feel free to contact us.